Okay, two key points to make from this question. Your formula sheet has the definitions of physics, okay? What it says in the formula is the definition of that quantity in physics. So look out for that. Also, on the face of it, they seem like pretty straightforward calculations, but there's extra physics in there kind of snuck in for you to apply. You've got to be quite fluent in applying ideas from your DC electricity to your thermal physics here. And they're combining them to make it a synoptic calculation. Tomatoes can be made into puree. Right, thank you. The puree is heated, okay, so we're talking thermal physics, are we? When the puree boils, its temperature stays constant, so we're talking about that latent heat idea. Energy keeps going in, temperature stops rising for a little bit whilst there's this change in state. Explain this observation in terms of molecular energy changes. So we do not want to hear, well, the energy is going to breaking the bonds between the atoms. That might have been okay in GCSE. It's not the level that we expect you to understand this at A level. So we're going to go ahead and go to our thermodynamics and find the bit about molecular kinetic theory. I've scribbled all over this, but this is essentially the definition of temperature here. Okay, it's a half mc squared, where c squared is the RMS speed of the particles. So in other words, it takes out of the equation any vector considerations, is 3 over 2 kT. So this is the definition of temperature as the average kinetic energy of the particles is proportional to the temperature. And 3 over 2 is obviously constant, and k is the Boltzmann constant. So these are constants. So what's happening in terms of molecular energy changes? Well, the average during the boiling kinetic energy of the molecules is constant. Now we can see that because, well, we've defined temperature here by saying temperature is proportional to a half mc squared. Now you don't need to say that for the mark, but I'm just trying to get the point that you can use the equation in the sheet to define what you are asked about in the question. Okay, well, my next point would be that what's happening instead then is that this energy is going towards raising the potential energy of the molecules rather than changing their kinetic energy. So I hope that makes sense. This is equivalent statement to that, well, the energy goes to breaking the bonds. Okay, so there's only really two types of energy. There's kinetic or potential. The energy here is not increasing the kinetic, it's increasing the potential. So during that boiling, they're not moving around any faster, they're just becoming at a different point relative to one another. They have a different energy level, they have a higher energy level relative to one another. Okay. What is the specific heat capacity of this puree? That's the next thing. So it's got a mass of this, that's okay, that's already converted. Boiling temperature there, something of energy, well, I'll just convert that straight into joules, thank you very much, before I do anything. Supply to bring it to its boiling point from a temperature of 21 degrees C. So we have a delta T of 80 degrees Kelvin or C. You probably remember the specific heat capacity equation from your GCSE, but hey, let's go and find it. Here it is in thermodynamics in heating. Okay, they've used delta theta, but it's the same equation. I don't want to work out E, I want to work out C, so let's go ahead and write it the right way around. Sorry. And put the numbers in. It's still worth doing this, guys. I know this is a simple step, and I could probably do this in my head, probably do this directly into the calculator, but if I did make a mistake, I've given myself that use of mark. 4926.8 joules per kilogram per degree Kelvin, I'm going to say. Alright, put that in there, giving it to probably 3 sig fig, as that's the data I've been given. And talking about mistakes, in fact the mark scheme had this wrong here because they'd used 100 in there. So I'm also just thinking to myself, is that a sensible answer? Roughly in the thousands of joules per kilogram per degree C, and higher than water. Water's 4,200. Yes, I think so. There's going to be some sugars in that puree. I'm quite used to the idea that sugar solutions maybe can contain a bit more energy per kilogram per degree C when at the same temperature. Okay, so the mass of the puree is reduced by boiling. The saucepan is heated by a radiant electric heater run from a main supply. Aha. Voltage of this. Okay, and a current of that. I know I've got a power now, don't I? Okay, from my equation sheet, and just because I've worked hard and I've practiced, and I can define what an electrical power is. And actually I know that an electrical energy is VIT, so I'll also scribble that down because I'm guessing, yes, they're asking me for a time. Right, okay, I can do this. Calculate the time taken to reduce the mass of the puree at boiling point by this. So this is my M that I'm talking about. This is the amount that has boiled. Specific latent heat of vaporization is this. And I'll go back to my thermodynamics bit and just remind myself that specific latent heat of anything is governed by this equation. E is L delta M. So let's scribble that down as well. Now I can enter this in here essentially because we haven't been told, but I'm guessing we're just going to ignore any waste effects because otherwise how are we going to do this? So I'm going to put VIT in there, rearrange everything for T, and now I can just sub my data in, checking as I go that I've got the right SI units. So this is all remarkably easy, isn't it? So just stick in my data here. It's a little bit too easy. It's a little bit disconcertingly easy for 4 marks on an A-level paper. So, well, what's going on here then? This V, let's have a little reread. Blah, 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 blah. Peak voltage. Peak current. Okay, so actually they have snuck in some extra physics in there, haven't they? So I need to go ahead and get my RMS voltage and RMS current before I do anything. So the RMS voltage is simply V0 over root 2, and the RMS current is also I0 over root 2. So let's just figure those two things out. 325 over root 2 gives me 229.8 volts. RMS current is 12.4 over root 2, which is 8.77. These are my 2 bits of data I'm going to use in here. Well, that's 230, isn't it? So that's good old mains voltage. Sneaky examiners, eh? Sneaking in extra little bit of physics there. $264 3 sig figs is okay. Seconds. I think that's just a case of being aware of checking, okay, how many marks is it worth. You're used to this type of question, probably even on a GCSE paper that might have only been worth 3 marks. They're going to be asking you to derive new equations from different areas of the syllabus. So you have to be resilient, you have to be quite fluent in those sort of year 1 definitions of things and be ready to, oh, I see, they've given me V and I, that allows me to work out a power.